previously, but over the last few years, the views about the superconducting phase of strontium ruthenate has completely changed. So in order to introduce that, I will first show you a timeline, if I'm allowed to switch my slides. Yes. I will first show you a timeline of the superconductivity in strontium ruthenate. It is a perovskite oxide that is isostructural to LbCO, and it has a highly 2D character. And actually, it was the superconductivity in this material was found while looking for other high TC materials. However, it is not a high TC; it has a very low TC of only 1.5 kelvins. Then, already quite quickly after the discovery of superconductivity, it was proposed that the superconducting ground state of strontium ruthenate is similar to that of superfluid helium-3, namely that it's in a chiral equal spin triplet ground state, where I note the pairing here. So this is a P-wave style of pairing. There's figuratively and literally two components to this. First, there's the triplet part. Triplet meaning that the electrons don't pair up with pairs of opposite spin, but actually pairs of equal spin. And there's the chiral part. The chiral part meaning that the orbital part of the wave function winds its phase, and you can think of this of the two electrons of the Cooper pair effectively rotating around each other. And since they can rotate either clockwise or anti-clockwise, it is proposed that the superconductor breaks down in domains of either chirality, and in each chirality the orbital phase only winds in one direction, and they are separated by a chiral domain. So this was the idea for almost 25 years, until 2019, when everything changed. But before I get to that, I will first explain a little bit more on why people thought this was a triplet chiral superconductor. So first, the triplet superconductivity. Quite early on, it was found by NMR night shift that the spin susceptibility is not suppressed. It's not suppressed in the superconducting state, indicating that there is a spin component to the system. Also, with polarized neutron scattering, similar effects were found, and so the spin susceptibility is not suppressed below TC. And a bit later, in 2010 or 11, I'm sorry, there was evidence found of half quantum vortices that can only be stabilized in a triplet condensate. This was found by cantilever magnetometry, where the half quantum vortices are stabilized by introducing an in-plane magnetic field to very small rings of strontium ruthenate. And interestingly, these fields are around 20 millatesla in plane. And this is actually coming back later in my talk. And what they found is these half-height magnetization steps corresponding to behavior of a half quantum vortex. So this is quite a strong body of evidence that that it's a triplet superconductor. Then the time reversal symmetry breaking, which is equaling the chiral nature of strontium ruthenate. The evidence for this was mainly the muon spin resonance experiments and polar Kerr effect that found local emergent magnetic fields below TC. And these local magnetic fields, they correspond to the orbital phase winding either clockwise or anti-clockwise. And well, since these electrons process around each other, they produce locally a magnetic field. So like I said, these are two local techniques. People have also searched for these magnetic fields using scanning squid and scanning hole probe. However, these were never found. So this was for a long time a big question why they couldn't be found by scanning squid and scanning hole probe. But now we get to 2019, when everything changed. So here I'm listing again the evidence for the triplet superconductivity and for the time reversal symmetry breaking. But then it was found in 2019 that actually the spin susceptibility is decreasing below TC, and that actually the previous experiment where it didn't was caused by a quite subtle effect of heating of the substrate hull. Then the polarized neutron experiments were also revisited, and it was found that actually the fields that were applied in this experiment were too high, namely that they were above the upper critical field and therefore pushing also the crystal to the normal state. Then again, the muon spin resonance experiments have also been revisited in strain samples, or while straining the sample, and it was actually found that this is still standing. So interestingly, the whole triplet picture that was around for 25 years is now out the door. But then again, some chiral superconductivity must still be there. And there was also published a large body of evidence, large body of experiments about the two-component nature of the order parameter, mainly from ultrasound spectroscopy and ultrasound velocity measurements, where it was found that the order parameter has to be two components. So two component you can think of, for example, in the P-wave case, that there's a right-handed chirality and a left-handed chirality. These are two components. But this can also be, for example, a chiral D-wave order parameter, an S plus D-wave, or like Kiefelsen and co-workers claimed in their quite nice paper about reconciling the diverse experiments that have been done over the years, that it could be an accidental degeneracy between a D-wave and a G-wave. So at the moment it's not so clear what the order parameter is, and this is a big open question to answer this actually. Then there's the normal state of strontium luthenate. For a long time people thought this is the textbook example of a Fermi liquid material. However, last year there was a quite nice experiment on thin films by Wu and co-workers, where they studied thin films in the shape of this sunbeam pattern. So these are 36 Hall bars in a lot of different directions. In total, 253 contacts. So imagine the poor PhD student wire bonding all of them. But the results were quite nice, because they found that there is a resistivity anisotropy in the plane that does not correspond to the crystalline axis. So this was a truly electronic nematicity. So we don't know anymore what is the superconducting state, how the superconducting state behaves. We don't know anymore how the normal state behaves. So, but the one thing that seems to be consistent over the years is that there is a two-component order parameter. So before I continue to our results, I will first highlight that most of these experiments are done on bulk. And if we are actually wanting to research these domains between different components of the order parameter and the domain while separating them, it is very important that we also look at microstructures. Since in microstructures we are able to possibly trap a single domain or possibly trap a single domain wall. And that is exactly what we did. So we'll show that we can trap the spontaneous formation of these superconducting domains, and this is definitely compatible with the two-component order parameter picture. So first I will tell a bit on how to create these microstructures actually. We do this with the mechanical exfoliation method that was developed for the production of graphene. It's also called the scotch tape or sticky tape method, where we take a piece of scotch tape and we cleave a larger bulk crystal into crystal flakes, and these crystal flakes we were able to deposit on a substrate. Next, we use e-beam lithography to contact these crystal flakes, and we can use focused, so we can do transport experiments on them. And next we do focused ion beam milling to mill these crystal flakes into microstructures of all shapes and sizes. Focused ion beam milling is often considered as a quite violent method. However, if you do it the right way, then you don't have to sacrifice sample quality at all, which is shown here, since if we cool down one of our crystal flakes, we often see very high residual resistivity ratios for our smallest structures above 100, and for the micrometer-sized ones, often above 300, with very, very sharp transitions at 1.5 Kelvin. And as you can see here, only 20 millikelvin makes a world of difference. So the transition is quite sharp indeed. All right, so now we can make all sorts of microstructures that have high quality. So the one I will highlight first is the ring geometry. Since if you have a ring geometry of an ordinary superconductor, so no unconventional superconductivity, no domains whatsoever, and you would thread a magnetic field through the center of the ring, you would not see any interesting behavior. However, this completely contrasts with what we see. What we found is that the critical current is strongly dependent on the magnetic field that threads the ring. And what we see is actually an interference pattern that is reminiscent of a squid interference pattern. Actually, it is a squid interference pattern. So that would mean that we are dealing with two weak links on either side of the ring. However, we have fabricated a very pure sample that has no intended weak links in either side of the ring. We didn't fabricate them, they're spontaneously there. Then the question is, if you cut one arm of the ring, you're probably going to see a Fraunhofer pattern. At least that is what you would expect. This is not something we see, but this can be explained since the width of the arms of the ring is roughly 3 to 4 times the coherence length. And since if you're dealing with these length scales, then the Fraunhofer interference pattern is turning into a Gaussian decay, rather a Gaussian decay. And when we fit these with Gaussian functions, they are definitely Gaussian. And you could say maybe this is an effect caused by the geometry. However, when we simply make a doubly connected sample, what we find is still the squid oscillations that we see in the ring. All right, well, you could say, well, maybe there's something fishy going on with the field. So therefore, we also obtained a detection of Shapiro steps, where we radiate our samples with a nearby antenna. And for both doubly connected and singly connected samples, so both one arm of the ring or two arms of the ring, we found these plateaus in the IV characteristic while radiating the sample, which are a clear signature of Josephson behavior. So this means that we are definitely dealing with spontaneous Josephson junctions that are appearing in these homogeneous rings. Then, what are these spontaneous junctions? Well, you could say these are maybe constriction weak links, since we're dealing with quite small microstructures. However, we are the width of the arms of the ring is still a few times the coherence length, so not small enough to act as a constriction junction. And furthermore, we see that there is no temperature dependence at all on the shape of the oscillations, whereas the current phase relationship of a constriction junction definitely has a strong temperature dependence, and therefore the shape of the oscillations would change. You could also say it's microcracks or crystal domains, but this is not consistent with the fact that we obtain very high residual resistivity ratios and very sharp transitions. And also under inspection under the SEM, we don't see any inclusions or whatsoever. You could also say this is persistent currents or current excited vortices. However, these would not yield Shapiro steps, because Shapiro steps can only be obtained for true junctions. So that is why we call them intrinsic weak links. Then the question is, what pairing does it suggest? Well, it can be modeled all in the chiral p wave according to the chiral p wave state, but really it suggests any two-component order parameter, since any two-component order parameter can break down on the microscale into domains where one component is favored over the other. So this can be modeled like this, for example. In yellow there is one of the components. Then at the domain wall, one of the components decreases in magnitude, so the wave function of one of the components, and the other is increasing. However, locally, the condensate is suppressed, and this acts as a Josephson junction between, for example, two chiralities in the P wave picture or two chiralities in the D wave picture. That doesn't really matter. So in any two-component order parameter, this can happen. And our collaborators in Antwerp actually carried out time-dependent Ginzburg-Landau calculations and found that in the size of microstructures that we are using, that two chiral domain walls could be stable in either arm of the ring, explaining the results. All right, so now we found what these spontaneous junctions are. Now we can examine them a little bit more. So this is the picture of the ring with two domains on either side. The domain walls are in either side of the ring, and therefore it acts like a squid. But back to the special properties of these types of junctions. For this special property, we have to apply a 20 millitesla along a 20 millitesla field in plane along the ring. And remember that this is the same field used in the half quantum vortex experiments. Then what we find is an anomalous hysteresis in the IV characteristic. So I will talk you through. We start at zero current, and we start increasing the bias towards the negative side. So what we see is a critical current where we start to go to the resistive state, and we find a retrapping current that is smaller than the critical current. This is fine, this can happen in overdamped junctions, so this is not something that is very special, let's say. However, when we go to the other current polarity, we see that the critical current is smaller than the retrapping current, which is highly anomalous. So we started playing around with this a little bit more, and what we found is when we wanted to repeat this experiment on the positive bias, we found that once we have switched from the low critical current to the high critical current, we are stuck in the high critical current. So after switching between one to the other, you will always find a critical current that is high and a retrapping current that is the same, namely also a higher retrapping current. So you only switch once. And the only way to reset this is actually going to the negative bias again. So here what we did is we sweep the current. After sweeping the current to the positive bias, we start going to the negative bias, and we start sweeping up the current, but we don't go all the way to this point where the two curves meet. So once we don't go to that point, we can keep sweeping up the current as much as we want, but we will always stay in this high critical current state. And actually, once we go past this point, then we switch and find ourselves in the low critical current state. So here again, if we prepared our sample by switching on the positive polarity, we can go to currents 1, 2, or 3, and we stay in the high critical current state. However, once we go to currents 4 or 5, we switch and find ourselves in the low critical current state. So instead of thinking of it as an anomalous hysteresis, actually what it is, it's a two-state property that we reveal using these in-plane fields. Where there's one state, the low critical current state highlighted in blue here, and the high critical current state highlighted in red here. and you can switch to them by application of current. Interestingly, when you reverse the magnetic field direction, you find that the polarity having the anomalous hysteresis also reverses. So there seems to be some symmetry in the system. We found that this effect is normally revealed by applying an in-plane field along the ring. So we thought it has to do something with the sample geometry. However, there are also different angles of fields where you see this behavior, and some angles that will never show you this behavior. So we're still trying to figure out at the moment why we see this, and exactly at what angles, in-plane angles, we find this. However, a possible explanation, apart from the sample geometry that might play a role, is that it might have a possible connection to the nematicity found in the thin films. Since if the normal state system has this electronic nematicity, and we found for some angles that there's actually this two-state behavior, they might be related. However, I think that is left more as an outlook. So now I will turn to my conclusions. We found this spontaneous Joseon behavior in singly and doubly connected samples, which we interpret as intrinsic superconducting domain walls between two parts of the sample, and probably also between two components of the order parameter. And we reveal an in-plane, by the application of in-plane fields, we reveal a two-state property which we do not understand at the moment. However, as an outlook, we're still trying to relate this two-state property to either the crystal axis or possibly even to this electronic nematicity. And with that, I would like to thank you for your attention.
Can you guess how many Joseon junctions do you have in your rings? Is it a single junction or some in sequence in parallel?
Yeah, it depends. I will show you this slide. This depends a bit on the temperature actually, and it also depends a bit on, at least according to the simulations, it depends on, for the chiral P-wave state, it depends on temperature and the dimensions of the ring. So in this figure here, you see the inner and outer radius normalized to the coherence length. And so each choice of inner and outer radius will give you one of a line through this, let's say, phase diagram that is temperature dependent. So once you go to the higher temperatures, the coherence length increases and then blows up at Tc. So you will go towards the lower left of this line, and for lower currents you will go to the upper right. And you see that, for example, for higher temperatures there might be two chiral domains, and for lower temperatures there might be one. And actually there's also this part of the phase diagram that we also try to probe, where there shouldn't be any. However, we found while making these samples that the necks of the ring can actually also act as Joseon junctions. But yeah, indeed, there can be a few Joseon junctions or one, but really depending on geometry and temperature.
I have a question. One of the slides showed speed characteristics at different temperatures.
Yes.
This one. Yes, this one. Yes, I wonder the high temperature curve, which 1.2 Kelvin. You have actually kind of summation of two curves. So there looks like you have two characteristics which overlap each other.
Yes. Yeah, sorry, this I should have explained indeed. This is, we plot for the lower temperatures, we plot the only the positive current polarity, and actually for the higher temperature I've also plotted the other current polarity. Since while actually doing these measurements, we sweep IV characteristics, and for the lower temperatures, the IC is quite high. So if we would sweep the full polarity, so the full current range, this would take a lot of time. And since these measurements per curve, they take, if you take a single polarity, they take, let's say, 12 hours to make. So then they would increase to 24 hours. So it's simply a time constraint. Whereas for the high temperatures, you can sweep, let's say, from -30 to 30 microamps, since the critical current is so low.
Okay. So as far as I can see, you don't have any signatures of patients.
Yes, indeed. Yeah, we didn't find anything relating to these patients. No.
Yeah, I think there are some questions from online listeners. Yes. Okay, please.
Yeah, can you hear me?
Yes.
Yeah, this is Adar Steinberg. My question is about the cohort of samples that you measured. So you're using exfoliated samples. So I wonder how thick do they exfoliate, and whether there is any variation which could be observed related to the sample thickness.
Well, strontium ruthenate is a van der Waals material, and actually the van der Waals forces between the layers are quite strong. And so, for example, for Bisco crystals, which is a material that is typically exfoliated, this high TC material, you find many flakes while exfoliating, and the thicknesses are between, for Bisco at least, are between, let's say, monolayers and bigger parts of the thicker flakes. Whereas for strontium ruthenate, there is not so much variation. I would say mostly you find flakes between 200 nanometers thick and 1 micron thick. Mm-hmm. These are the thicknesses that pop up the most. And with this, they are crystal flakes, yes, on one way, yes, but they can still be considered as true bulk-like crystals, although simply much smaller. And since they are smaller, they are easy to structure using focused ion beams, and therefore give access to these microstructures. We did.
So you did. So that you mean there is. So my question is whether this experiment was carried out on various flakes with different thicknesses.
Yes, yeah. We did carry the ring experiment out on thicknesses between. Well, one sample was indeed 100 to 200 microns thick, and actually before I started my PhD, Kaveh Lahabi, who's also here in the audience, he also microstructured bigger crystal flakes that were, I think, up to a couple of microns thick even, and then even the squid oscillations still persist.